This video is going to run through a review of linear graphing and the skills that are presumed knowledge for Module 3 Graphs and Relations in Further Mathematics. So firstly, with our linear graphs, we need to have an understanding of gradient. So remember, gradient is always measured as rise over run. And we tend to talk about gradient in terms of 2 points on the graph, and we label those as x1, y1 for point 1 and x2, y2 for point 2. So that gives us 2 points of reference for all of our further work. So some key things about gradient. We have different types of gradient. So obviously if we look at this first example here, we can see our line is travelling up our page. So as we are moving along the run, we then have to travel upwards for the rise. So that gives us our positive gradient. By the same token, for the second example here, when we have our run across, we're actually dropping down to that run. Well, the other way of thinking of it is we're going out and then down to the second point, and so that gives us a negative gradient. The third example here, the horizontal line, that means we have a flat gradient. So the gradient is not going up or down, so we actually say that that is a zero gradient. There's no change in the rise as we're running across. And finally, the fourth example, the vertical line, this gradient is so steep that we can't actually define what its value is. So therefore we say anything that is a vertical line actually has an undefined gradient because it's rising infinitely over a run of 0. So calculating our gradient. Sometimes we are given a graph and sometimes we are given points to calculate our gradient from. So remembering that our gradient, also known as slope, is always measured in terms of rise over run, and that rise over run can be written as y2 minus y1 over x2 minus x1. So the first thing we need to identify is 2 points on the graph. Now I always, where possible, use points that run through grid lines because it means you can be accurate. So here we have our first point here at 0, 6, remembering our coordinates are always given as our x coordinate first, then our y coordinate, and a second point here at 8, 0. So then it's just a matter of substituting in those values to find our gradient. So we quite often use an m to represent gradient in terms of our linear graphing, and we just sub in. So y2 would be 0 minus y1, 6, divided by 8 minus 0 for our x coordinates. And so here we get negative 6 over 8, and that will cancel down to negative 3 on 4, or negative 0.75. Okay, so the other skill we need to know is how to sketch and how to plot graphs. Remember, the key difference between a sketch and a plot of a graph is a sketch is just a rough estimation. So obviously we need to use a ruler and draw a straight line, but we just need to show 2 points on the graph or any key points, and they would be considered axis intercepts, either the x-axis or the y-axis intercepts. If we're plotting a graph, that means we've been given a scale to work to, and the graph must be drawn to scale. So in order to sketch a linear graph or to plot a linear graph, we need 2 key points, and we just draw a straight line through those. So with this equation here, y equals x plus 1, we need to identify the key things from our equation. So in this format, we actually have our gradient always is the value in front of the x, and in this case our gradient would be 1. And our y-intercept is always the value that's added or subtracted or on its own. So in this case, our y-intercept, which we use a c to represent, would be at 1. So that tells us if in this graph here, if I was to add a little scale of 1 just here, I have a y-axis intercept there. Now using my gradient of 1, that means for every 1 unit I come out, I'm going to go up my graph 1 unit, so I can put a second point there. And similarly, if I wanted to make sure and add a third point, if I come back 1 unit, I can drop down 1 unit and put in a third point there. Now obviously you would use a ruler, and I'll do my best here with this pen, and that would be our line of y equals x plus 1. In the second example here, we now have an equation given to us in what we call intercept form. So intercept form actually allows us to easily find the x and y intercepts. And by doing that, to find our x-intercept, we actually let y equal 0. And that will allow us to find a key point. So in this case, we would have 2x plus 3 times 0 equals 6, or 2x equals 6, so x equals 3. So we can put our our x-intercept at 3. So let's make that 3 just there. And for our y-intercept, we let x equal 0. And so that would give us 2 times 0 plus 3y equals 6, so y equals 2. And working up our graph, we can put our second point there at the y-intercept of 2. And again, using a ruler, we just draw a straight line through those 2 points, and that becomes our graph of 2x plus 3y equals 6. Alternatively, we can rearrange that equation so it's in gradient form, like the previous question, and then just plot using our y-intercept and our gradient as well. But we have the options there. Remember, if you did want to turn this into gradient form, you could just simply put that into your calculator and ask your calculator to solve for y, and that will rearrange the equation for you. Okay, the other skill we need to have is determining the equations from graphs. So here we've got the same graph as we had earlier on, and we need to work out what the equation of it is. So key components of our equation are going to be, if we look at it in terms of gradient form, so y equals mx plus c, we need to work out what our gradient is, and then we need to work out what our y-intercept is. Now from the graph we can see our y-intercept is 6. So we already have part of our equation. What we need to work out is our gradient. So you might remember from previously, but we'll run through this example again. One point there at 0, 6, a second point at 8, 0. So my gradient is going to be 0 minus 6 divided by 8 minus 0, and that gave us negative 0.75, or negative 3 on 4. Now putting that together with our y-intercept, we end up with an answer of y equals negative 0.75 x plus 6. So our gradient negative 0.75 and our y-intercept of 6. In this example, we aren't actually given the value of the y-axis intercept. So there are a couple of different ways of working out our equation. We still want to end up in the form y equals mx plus c. So I know that because I have 2 points here, I can actually find my gradient. So let's find that first. Gradient equals y2, so 8, minus y1, negative 2, divided by x2, 2, minus x1. Now remember, 2 negatives make a positive, so that actually means I'm adding. So I would end up with 8 plus 2, 10, divided by 2 plus 3, 5. So my gradient equals 2 in this case. Now from this point you have a couple of different options. What I tend to use, the method I tend to use, is using the formula y minus y1 equals m times x minus x1. So that means from my graph and from the working I've done previously, I'm taking my value of the gradient, m, and I'm taking one of the coordinates. So let's use y1 and x1 as this first coordinate here, the negative values. And I'm just substituting those in. And again, you can substitute them into your calculator, ask it to solve for y, and it will rearrange the equation for you. So this would become y minus negative 2 equals 2 bracket x minus negative 3. And so we just simplify that a little bit before we move on. 2 bracket x plus 3. Now in this case we should expand that bracket simplify and then bring the y across, the 2 across, so y is on its own. Again, you can use your calculator to do that working for you. And so when we expand and simplify, we end up with y equals 2x plus 4. Okay, a couple of special properties that we need to have an understanding of, and this is more about gradients than anything else. So I have two lines here. I can see the equation for the pink line is y equals 3x plus 1. The equation for the blue line, it is actually a parallel line. So it means that the two lines will never touch, they'll never meet. And a special thing with parallel lines is that their gradients are actually equal. Okay, so the gradients are equal to each other, which means that the gradient of the blue line will be the same as the pink. And we know that the gradient is the number that goes with the x, so our gradient here will be 3. From the graph, we can also see that the y-intercept for the blue line is at plus 1. So the equation of the blue line will be y equals 3x plus 1. So we can see the 3 and the x in both equations, and that tells us that the two lines should be parallel. Another property that we need to know about is perpendicular lines. So perpendicular means that it is at right angles. And sometimes we use a symbol like that to represent that they actually are perpendicular lines. So we have a little right angle in here. Now, a special property with perpendicular lines is that the product of the two gradients equals -1. So that means that the gradient of the pink line times the gradient of the blue line will equal -1. Now, that can be useful, particularly if we arrange the equation in this form. So we can say the gradient of the blue line, or line 2, is equal to -1 divided by the gradient of the pink line. So in this case, that would mean the gradient of my blue line is equal to -1 divided by 3, because our gradient here is 3. We can also see from the diagram that the y-intercept of that blue line is also at plus 1, so that means its equation will be y equals -1 on 3x plus 1. And you can also write that as -x on 3 plus 1. We don't want to make that third 1/3 into a decimal, because where possible we like to leave them as exact answers. So we will leave it as a third at the front there. Okay, linear modelling. A lot of the next part of this unit actually relies on problem solving or linear modelling. So taking real life situations and applying a linear rule to them so that we can solve for different scenarios. So most of us see this as a little bit frightening because we don't like problem solving or we struggle with worded type questions. But there are a couple of sort of key things that we can look at to help us out and make sure that we're on the right track with these. Okay, so let's have a look at this example. A candle burns down at a rate of 2.5 centimetres per hour. If the candle is 20 centimetres long when it is first lit, what will the length be after 4 hours? So in this scenario here, remember we're always trying to apply a linear model. So that means we're trying to construct a linear equation using the information that's given to us in the question. So using this information here. So if I think about, if I jump down to question B, they're asking us actually to write an equation there. So they're saying the length of the candle after T hours. So we want to write an equation where we've got L equals something something T. Okay, so we need a gradient value and we need a y-intercept value. So the thing that's changing over time, because time is our x-coordinate, if you like, or our independent variable, the thing that's changing over time is the rate at which it's burning. So it's decreasing by 2.5 centimetres per hour. So our gradient will actually be -2.5. And then our y-intercept is, if you think of it as your starting point. So here, our candle started at 20 centimetres, so our y-intercept is actually going to be plus 20. So that gives us the equation there, L equals negative 2.5t plus 20. So how long will the candle be after 4 hours for part A? So in part A, we could either have just worked out that, well, after 4 hours, it's going to reduce by 2.5 for each of those, so a total of 10 centimetres lost, and 20 as a starting length minus 10 would leave us at 10 centimetres. Or we could use our equation we've just created. So part B, we've done our equation. Part C, how long will it take the candle to burn out? So what are they asking for? They want to know when will the length equal 0. So we need to solve an equation here. We want to say that our length is 0 and use our equation 2.5t plus 20 to solve for that. Now again, anything that's requiring you to solve, you can put it in your calculator and solve. Okay, if it's something simple and you know you can do it by hand, then by all means we do that. And so by solving that equation, we end up with t equals 8. So that tells us it takes 8 hours for the candle to burn down to nothing. That's assuming that the candle could keep burning until it had no wax left at all. Part D, construct a graph of L versus T. Okay, so we don't have a scale marked here, so we just need to draw a sketch. Now, we know that when the graph starts, so when the candle starts, it is 20 centimetres long, and we know that it takes us 8 hours to get down to 0. So that 8 hours and 0, this information here, gives us our x-axis intercept. So if we actually put in, well, we know it's going to hit 0 after 8 hours, and I know it's going to start off at 20 centimetres long, and let's mark in a scale here. So 20, I'm just going up by 5s, and across the bottom I'll go up by 2s. Then I can quite easily draw my line in, again with a ruler, and I'm only going from point to point. Okay, and there's my sketch of my graph. From that graph then we could potentially use it to find other values, or more reliably than a sketch by hand would be using our equation that we constructed in part B. Another application that we need to know about are simultaneous equations. So with simultaneous equations, basically if I had to find when the two equations equaled each other, so when does 4x plus 3y equal 10, when does that equation equal y equals 3x plus 1, then I can either solve by hand methods of elimination or substitution, or what I'm actually also doing is finding the intersection point of the two graphs. So I can do that by graphing the equations in my calculator. The other method using my calculator is actually to use solve, and some of you will have done this before, where we actually can say, well, let's solve the two equations, and I would solve 4x plus 3y equals 10, and then I would actually leave a space in my calculator, pressing the space bar, type the word and, another space, and then the second equation, y equals 3x minus 1. And I would just tell it to solve for y, or x, doesn't matter, and it will actually give me the values there. So it would tell me that x in this case equals 1 and y equals 2. So I never have to use elimination or substitution to work it out by hand. Obviously sometimes that's going to be quicker, but you always have your calculator in every assessment. So in terms of simultaneous equations, what you need to be aware of is if you're asking to find the point of intersection, or you're being asked to find when two equations equal each other, this is the same thing. We tend to start then using this as applications of break-even analysis, which you may have touched on in Year 11, but we will go through in more detail again this year throughout this module. Okay, so I hope that was helpful. We'll continue to put up other examples for things throughout linear, but this is just a bit of an overview of the things that we expect that most of you will be pretty comfortable with coming into this topic.